Welcome to this lecture on multiple kernel learning, MKL. So the motivation for today's talk is to discuss what happens when you have several candidate kernels for a given problem, and you're not sure which one to pick or how to combine them. Right, so this is a bit of consequence of the previous lectures, where we have seen that there exists plenty of different kernels for any type of data. So even only for graphs, or only for strings, or only for vectors, there already exists many possible choices if you're confronted with a problem. And in addition, there are also many cases where you want to solve a problem and your input data can have different forms. So we talk sometimes of multimodal data. Just to take an example, in biology, in life sciences, when you want to predict something about a protein, which is a molecule, for example, to predict the function of a protein, you need to describe the protein with some features. And a protein can be described through, for example, its amino acid sequence, then it's a text, or it can be described by its 3D structure, then it's a shape, or it could be described by its position in a protein-protein interaction network, and then it's a node in a network, right? So for each of them, we have seen different kernels, and the question is, at the end of the day, when you want to train your model to predict the function of the protein, what do you do? Which kernel do you choose? How do you combine them, etc.? So we will discuss a bit this question, and we will discuss it in a specific context of when you have to solve a supervised machine learning problem. Of course, there are many extensions or many variants when, for example, you solve a non-supervised problem. But here we'll stick to the simplest setting, where we assume that you want to train a function that goes from your space of data, capital X, to the real numbers. So this could be used for classification or regression, but the function you train goes to R. It's typically a function in an Rkhs. We'll assume that we have a training set of points, so x1, y1, x2, y2, up to xn, yn. And we'll assume that the problem, so the algorithm we only use, is an algorithm that solves an optimization problem over an Rkhs. So if you give a kernel over X, then the algorithm solves the minimization when f is in the Rkhs of the kernel of some risk function of f plus lambda times the square norm in the Rkhs. And so the risk function will be typically one of the ones we have seen before in this course. If for the risk we take the sum of differences between the predicted function and the y's, we obtain kernel ridge regression. And if we choose different loss functions, like the hinge loss, we get SVM, or the logistic loss, we get kernel logistic regression. All right, so all these settings are abstracted away here. They are summarized in the function R, which is the risk function, and that depends on f. And I will just notice that I use the notation fn, with n, to denote just the vector of values that f takes on the endpoints. Okay, so the question is, when you solve this, when you have this algorithm and you're given several kernels, what do you do? So the simplest answer, I would say, is, maybe the simplest is you just pick randomly one kernel and you train your model and you're done. But it's not very smart. So the second level, maybe to say, let's try to aggregate the different kernels. And we have seen plenty of operations for aggregation, right? When you have kernel functions, you can do the sum, the product, the exponential, etc. So here we'll just investigate maybe the simplest idea, which is to sum the kernel and say that if you start with capital M different positive definite kernels on the space X, then you can define the kernel K index S as the sum for I equal 1 to capital M of Ki. Right? So from the first lesson of this course, we know that as a function, this is a positive definite function. So it's a valid thing to say I have several kernels, I add them up together, and I train a model with the sum kernel. One question is, can we try to understand what we do when we do that? So the one easy answer, I would say, is that that if you see each kernel as an inner product, because they are positive definite, so if you call phi I, for example, the mapping from X to some Hilbert space, that could be the Rkhs, or any valid space where the kernel Ki is an inner product, then you notice that when you sum the kernels, it means that you sum the inner products, And so summing the inner products is the same as doing the inner product of the concatenation of the phi i's, right? It's trivial. The proof is here. The inner product of a concatenation of vectors is the sum over the entries of the product. So you can do the sum per block and obtain that the inner product of the concatenation is the sum of the inner products. Right, so this gives a first understanding of what happens when you take the sum kernels in terms of where you embed the points. You can think of it as saying, if I have several kernels, each of them defines a feature space. When I decide to use the sum kernel, it means that I concatenate the feature spaces. So potentially this could be good if you think in terms of features. For example, coming back to my example of proteins, if you believe that there is some information in the protein sequence to predict the function, and some other information in the protein structure to predict the information, and also some other information in the protein-protein interaction networks, in the position of the protein in the graph, then if you just sum the three kernels together, you can think of it as creating a big vector where all the information about the sequence, the structure, and the network are combined, and therefore potentially a model trained on the sum kernel can learn a model that will combine information from the different sources. So this specific example, by the way, has been followed by many people. I just cite one old paper, but there are many such examples. So long story short, this is a paper about multiple genomic data integration. So here the problem solved is not predicting a function, it's predicting interactions, but it's still a supervised machine learning problem. And long story short, you see here ROC curves. So it compares different models in terms of how well they predict. And the thing you have to believe me about is that each curve represents a different kernel. So you have several kernels, and one curve, which is the base curve, is the sum kernel. Right? So the individual kernels are exactly as I said before, kernels that depend on protein, what's called expression, interaction, localization, etc. So think of them as individual kernels that capture some information about the protein. And if you just sum them together, you get a significant boost, in this case, on the performance. Right? So this is a super simple operation, just sum the kernel, but it's not stupid. It's just like you concatenate the features, and if you have information in the different kernels that can be aggregated together, then you can have significant boost in performance just by doing that. No need for any fancy things. So we will see later more fancy things, but already doing the sum is a smart operation. All right, so we have seen that when you make the sum of the kernel, you can think of it as concatenating the different feature spaces. So that's one viewpoint. Let's say the geometry viewpoint in terms of what is the space where the data are embedded. Now let's try to clarify as well what's the operation you do in terms of functional space. So in particular, what is the RKHS and the norm in the RKHS that you define when you do the sum of the kernel? Because remember that when you do kernel methods, it's nice to think in terms of features. So just to know what are the features you create. So here we say when you have several kernels, you combine all the features. But it's also very important to understand what's the norm in that space, because the importance of regularization is central in kernel methods. So you need to know, even though you combine all the features, what do you say in terms of what's the norm of functions in the RKHS to know if they can use all the features, or for example, if they can just focus on some of the features because of regularization. Right? So it's important, and we will do it now. It's important to understand not only the feature space, but also the geometry in terms of what's the Euclidean norm in that space, or equivalently, what's the RKHS norm in the RKHS. And so we have this theorem here that says very simply and clearly what the RKHS is, or at least what the solution is when you train with the sum kernel. It says that when you train a model with the sum kernel, so KS is the sum kernel, then you estimate a function f star, which, without surprise, can be decomposed as a sum of fi star, where each fi is in one of the RKHS. So if you have m kernels, you have m RKHS, and the function you learn is a sum of functions, each of them belonging to one of the RKHS. Right? So it's not surprising. It's just the fact that the kernel is the sum, the feature space are concatenated. So when you make a linear model there, you can decompose it as a sum. What's a bit more interesting is what's the norm. And here we see that the last equation shows you what problem you solve in terms of f star. So f star is the solution of minimizing over all the candidate set of m functions, so one function in each RKHS, of the risk of f star. So remember that the sum for I equal 1 to m of f in is just f star. So no surprise here. You just try to find an f star that has good performance. But the penalty is the interesting part in this equation. The penalty is just the sum of fi squared. Right, so it's not surprising here that we have the sum of the fi squared. If you think of them as, different feature spaces which are concatenated. However, what's interesting here, and there is something a bit important to see, is that here we have a minimization over f1 fm of the sum of fi squared. Right, so this means that, for example, when you have a function f star, it may possibly not be decomposable in a unique way into fi star, and the norm of f star is the minimal way, so the minimal norm you can get when you decompose it as a sum of fi star. So by the way, for the students of the master MVA in 2021, there was a homework where you proved this fact for m equals 2. So we're going to prove it again, and we're going to prove a slightly more general thing, which is, in fact, that if you don't only do the sum, but if you do a weighted sum with non-negative weights, so if you consider a kernel k eta defined as a sum of eta I ki, where the etas are non-negative numbers, then you have basically the same story, meaning that the space of functions you look into is the set of functions f star, which decompose as a sum of fi star. So no difference here. When you put weights, you don't change the feature space. Think of it in terms of concatenating feature vectors. When you put weights, you still have the same features, except you give them different weights. So the space of functions is the same, but the only difference when you weight a kernel is that the regularization is different. And therefore, this is why I said earlier that we should not only look at the feature spaces, what are the features which we use to make the prediction, but also what's the norm in the feature space. Because as you can guess, when you change the weights eta, you get very different kernels and you can get different behavior. So this is because of the regularization. All right, and so the regularization, this theorem says that the L2 norm, sorry, the squared norm of f star in the RKHS is the minimum over f1 to fm, so the minimum over the different ways to write f star as a sum of kernels of functions in each RKHS of the sum of the square norm of fi in the RKHS ki divided by eta I. All right, so in particular, this theorem is just a strict generalization of the previous one, because when you take eta I equal to 1, you recover the sum kernel and the equation we had in the previous slide. All right, so we're going to directly prove this theorem. So as I said, for the students, we already proved that a few weeks ago as a homework, but here we'll prove it again and using slightly different techniques, which will be a bit faster, I would say, than the generic proof we had in the homework. Because here what I will do is that I will not completely describe the RKHS, I will just show that the solution of the optimization problem when we work with the weighted sum kernel is this solution. All right, so let's go through the proof. It's not complicated. You can follow it line by line. So what we have here is just to say that if we start from the end, so we start from this formulation when we minimize the risk of the risk over the product of the RKHS. So we have n functions, and we say how to pick n functions that minimize the risk of the sum. So the sum at the end will be f star. Plus lambda times the sum of fi squared over eta I. And our goal would be to show that when you do that, you obtain a solution, which is the same as the one you obtain when you just solve your simple initial problem with the kernel sum of eta I ki. All right. So first comment, you see that R is convex. Here we have strictly convex functions, the square norm. So this is a strictly convex optimization problem. So there's a unique solution if in F1, Fm, etc. And in particular, we can use the representative theorem in each RKHS to show that each Fi can be written as a sum of, so because I is the index of the function, I will use a second index j, and write that the function fi of x is a sum for j equal 1 to n, the number of points, of alpha star ij ki of xjx. Right, this is the representative theorem. Now the question, what we will want to do is to clarify what are the alphas for different functions, and if they are the same or up to the eta, then this will be simply equal to a sum of alpha kernel sum. But here, for the moment, there is no kernel sum because we have different alphas, possibly for the different Fi's. All right, so, but still knowing that the alphas exist, so different alphas for the different functions and the different points, we can just rewrite our optimization problem in terms of alpha. So we just replace Fi by Ki alpha I, this is standard, and we replace the square norm in the RKHS of Fi by alpha I transpose Ki alpha I. And now we know that we just need to solve this problem in alpha, which is a finite dimensional optimization problem, strictly convex. Convex. Okay, so here we'll do some standard duality arguments in order, to move forward a bit. What we'll do is just because we have, if I come back here, you see we have alpha both in the risk and in the penalty. We will use a standard approach to derive a dual optimization problem, which is to separate the two terms by adding a variable, which we will call it u, and then do a Lagrange duality to rewrite this as a maximization problem. Right, so how does that proceed? We just replace, we introduce a u, and we say that optimization problem is equivalent to minimizing the risk over u plus the lambda times the penalty over alpha under the constraint that u is equal to fi, and so it is equal to ki alpha. Right, so we have added this variable u. And one reason to do that is that now we have a minimization problem over more variables, but with one constraint. So we can write the Lagrangian of this problem, and because Slater's condition hold, write the dual function. So the Lagrangian is minimizing the same function over ul alpha plus some Lagrange parameters, gamma multiplied by the constraint, so u minus the sum of alpha, ki alpha I. Right, and so this is the primal Lagrange formulation, and by Slater's condition, we know that strong duality holds here, so we can basically inverse the mean and the max, and we write our initial optimization problem as a maximization over the Lagrange parameter gamma of a function of u and alpha, which is a mean over u and alpha of this big equation. And so if we have done our job correctly, the minimization should be easy to solve. So we will do it now. We will try to compute the minimum in u and minimum in alpha of this as a function of gamma in order to derive the dual problem, which will be a function of gamma. All right, so the minimization in u, as I said, is easy because it's the minimization of the risk of u plus a linear function in u. So of course, it depends on what you choose for r. If it's the least square, or if it's so the squared error, or the hinge loss, or the logistic loss. But we'll make this a bit abstract and general because we know that as soon as R is convex, that minimizing R plus a linear function of u defines a new function, which is called a Fenchel dual. So for any convex function R, we can define the Fenchel dual, which is R star of v, defined as a supremum of u transpose v minus R of u. This is a standard definition, and for any of the R I mentioned, you can compute by hand the Fenchel dual. And so we can use this notation R star to rewrite our minimization in u in terms of R star. So we just have to be careful about the sign, but write the minimum as minus the maximum of the minus, so that we see a max appear. And the max is used in the definition of R star. So this would be negative R star of something. And the something, again, you have to be careful. The something is minus 2 lambda gamma. Right, so the minimization in u is a function of gamma, which is minus R star of minus 2 lambda gamma. The minimization in alpha is even easier. There is no R anymore. We just have a quadratic function in alpha. So just set the gradient to 0, just do the computation by yourself, and you will find that the minimization in alpha gives a simple function of gamma. It's a quadratic function in gamma, minus lambda eta I gamma transpose ki gamma. And the minimum, so the link between the primal and dual variable, is that when you minimize this, you know that the minimum is reached for alpha I equal to eta I gamma. Right, so this is the standard thing we've done. We have written the Lagrangian, and here we compute the dual function, if you want. So we minimize in U in alpha with no constraint to obtain a function of gamma, which would be the dual function. All right, so putting it up together, we obtain that the dual problem is a maximization problem in gamma. Gamma is the dual parameter, which is a sum of two terms. We have the R star, so the differential dual of R, and we have the quadratic term. All right, so let's look at it for a second. First comment we can make is that, so this is the dual problem you solve when you train, sorry, if I come back, when you solve this problem, which is minimization over f1 fm of R of the sum plus lambda times the sum of the square norm over eta I. So you may wonder, what if I just had one kernel, which would be the kernel k eta, right? If you just train with kernel k eta, then you can use the same formula, but here there will be just minimization over one function, f, which is in the RHS of that kernel, of its risk, plus lambda times its square norm. So you can make the same derivation with just a single kernel, so n equals 1, and no weight, so eta equal to 1, and this would give you a standard SVM or kernel ridge regression. Right, so if you do the same derivation with a single kernel, you will obtain the same function, right? You will obtain exactly the same dual, but the only difference is that there is a single kernel, so m equal to 1, and eta is equal to 1. So if you see in this equation where the kernel appears, it just appears here, right? So it means that the only contribution of the kernel is to change the quadratic function of gamma. And if you just have one kernel, this would be the sum of eta I, ki would just be the kernel you use to train. Okay? So this is what I write here. If you just train with the kernel k eta, the dual problem you get in gamma would be the same problem where you just have k eta. And so what you see here is that if you decide to use k eta, then the two problems are the same. Either you train just with k eta to get the second formulation, or you train with m kernels and the weights, and you get basically the same function because you recognize here the kernel k eta. Right, so this is a first equivalence between either solving this full problem over m RHS jointly. So when you solve all this, you obtain a dual problem that gives you a gamma, and you obtain the same dual problem, and therefore the same gamma, if instead of solving this big problem, you just solve one problem with a single kernel, which is k eta. Right, so now we need to check that. So we know that training with, solving this optimization problem is the same as solving one problem with k eta in terms of dual variable. And now we need to check that once you have the same gamma, you recover the same function, and you can write that f star is the sum of the fi's. Right? So the question is, from the gamma you get, for example, let's go back to our problem where we have the sum for I equal 1 to n. Once you solve the dual problem and you get the gamma, so let's call it gamma star, then we know from the analysis of the Lagrange dual problem that you recover the alpha i's by the equation alpha I star is equal to eta I times gamma star. Right? This was the conclusion of the minimization in alpha when we derived the dual. So this means that the function fi star, we know by construction, is the sum of alpha star ij times ki of xjx. And so if we replace alpha ij star by its formulation eta I times gamma star, we obtain a new formulation where the interesting thing is that instead of alpha ij, so potentially you have n different points and m different kernels, so you have n different alpha i's. But basically, what this equation says is that you don't have nm degrees of freedom. You just have a vector eta I, which is given a priori, and then you have a vector gamma, which is just a vector over the points, right? It has dimension n, and so all the alpha I are proportional to each other. So I mean, this comes from alpha I star equals eta I times gamma star. But this is a key property, which tells you that even though there are potentially n different vectors alphas, each of dimension n, so you potentially could have any ways when you just apply the representative theorem over the functions f1 to fm. In fact, what we have shown is that all these vectors alphas at the optimal are proportional to each other. Right, so there's a big reduction. In fact, if we had to solve it, there are not nm free parameters, there are just n plus m free parameters. And so, in particular, if you look at this equation where you have fi star, then if you sum all these fi star together to define a function f star, then you get a sum over I and j of these eta I times gamma j star, and so you can just, because you have two independent sum, you can just sum in I to obtain to put together the sum of eta I ki, which by construction is k eta, to derive that the function you get. So when you define f star as the sum of the fi stars, which is the function which is in the in the risk, so the function you train, which is the sum of the fi's, turns out to be the sum of gamma j star times k eta of xjx. Right? And so this equation is exactly the equation you would get if you trained a single model with a single kernel k eta, because you know that if you just train with k eta, you know that the solution is given by f star equals the sum of gamma j k eta of xjx, where the gamma j solve the dual problem that we saw earlier, right? So in conclusion, what we have seen is that when you solve the big optimization problem over n functions, you obtain a dual problem, which is the same dual problem as if you train with just k eta, so you have the same gamma. And the second thing is that the function you obtain, so the sum of fi star, is also the sum of gamma j k eta. So this is also the function you would get if you just train with the kernel k eta. Right? So this concludes the proof of this theorem that says that when you solve the optimization problem over n functions that I write in this slide, then the solution you get, so the f star, which is the sum, is the same as the one you get if you just train with one kernel, which is the sum of eta I ki. All right. So again, there is another way to prove that, which is a bit more general, which is to study in full generality the RKHS of eta I ki, and I leave it to you as example, as exercise if you didn't do it before. But you see, we cannot use exactly the same proof, for example, because we don't have a notion of risk. We just say, in fact, the RKHS of the sum kernel is the direct product of the direct sum, of the RKHS, and the norm is this one. All right. So what we've done so far is to say, when you have k kernels, you can just sum them together to obtain a potentially good kernel, and you can even do a weighted sum if you want. If you have some prior knowledge that maybe one kernel is more important than another one, some features are more important, you may decide to train a weighted kernel, and we have shown that when you train with the weighted kernel, we can describe precisely what happens. You train a function that has a small risk, and that's regularized by this function, which is a weighted, if you want, a weighted sum of square norm in the RKHS. So a next step would be, well, how do you pick if you decide to have a weighted kernel, how do you choose the eta? Right, so as I said, you may start by thinking, well, I have some prior knowledge, maybe that some etas should be large, some others should be small. But because we do machine learning, you may also think that the eta could be considered as parameters or hyperparameters that maybe you should optimize, or you should let the data choose by themselves. So the question we'll investigate now is it possible to learn the kernel, in the sense that, for example, it's possible to automatically learn the optimal weights that you should use when you train with the weighted sum of kernels. And so if it's possible, what should be, for example, the objective function, and how do you solve the problem? So we'll present one answer to that question, which has given rise to a number of interesting developments. And the answer is that maybe we can just use the same objective function as the one we use with a single kernel. Right? So we have this theorem here that I will explain. But basically, look at this equation here. There is a minimization problem for f in some Rkhs of the Rkhs plus lambda, the square norm of f in H. So this is really what you do when you train a model in an Rkhs. When you have a kernel, you solve this problem. And now we're discussing the question, if you have different kernels, what could be a good objective function to compare two kernels, for example? So intuitively, if for one kernel you think that this minimum value is good, like you want it to be small over the functions f, then it's tempting to say that if you want to compare two kernels, you may also compare this value in terms of the kernels. So for each kernel you solve your problem, you get a minimum value over f, and then you say, well, if I have two kernels, maybe the one that has the smallest minimum is better, because if we believe that, here in the risk there is some squared error, for example, then some regularization, you would say that if I have several kernels, I would like to pick the kernel with the smallest square. Right? So this raises the question of what's the role played by the kernel here. We see that the kernel is hidden in the Rkhs. And what we're going to prove is that this function, so the minimum value of the risk of f plus lambda square norm of f as a function of the kernel is itself a convex function of the kernel. Right? So it's a convex function, in particular of the kernel matrix here, because we just the kernel just plays a role through the kernel gram matrix when we define the risk and the Rkhs norm, and therefore we're going to show that this is a convex function. So once we show that, this means that maybe it's possible to jointly learn the kernel and the best function in the best Rkhs by minimizing our standard objective function over f and k jointly. All right, so how do you prove that this is a convex function? It turns out that if, for those of you who have some background in optimization and who are familiar with duality, etc., this is almost trivial. And this is proved here in 3 lines. The proof just amounts to rewriting our, the value j of k. So the j of k is the value corresponding to the minimum over f of the risk of f plus lambda times the L2 norm of f, sorry, the Rkhs square norm of f. And we have seen in the previous proof that this value can be also rewritten in a dual way as the maximum over gamma of something, which was a sum of some negative r star minus a quadratic function in gamma. Okay, and the interesting part in the equation is that we see here very clearly where the kernel is hidden. Right? If I take the primal form, the kernel is hidden in what is the Rkhs and what is the norm in the Rkhs. Now, in the dual, the kernel just plays a role in the second term, which is a quadratic function in gamma. Right? So this means that if you change the kernel, you don't change r star, you still optimize over the same space, which are the n-dimensional vectors. And the only thing you change is the second term, the minus gamma transpose k gamma. And so now we have to think, how does that depend on k? And we see that so if there is no max here, if you just say for a fixed gamma, we see that this function is a linear function. Sorry, the second term is a linear function in k. So the total r is a affine function, right? It's a constant plus linear function. And so basically there is a standard result that tells you that when you have an affine function, it is flat and therefore it's convex. And now if you maximize this function over gamma, it means that for each gamma you have an affine function. So you have one of them, a second one, a third one, etc. And there's a generic function theorem that tells you that the maximum of convex function, so each affine function is convex, and when you take the max of two convex function or any number of convex function, you obtain a convex function. Right, so proof is quite obvious just by writing the dual of j of k and seeing that the dual j of k is an affine and therefore a convex function of k. So when you maximize it over gamma, you're even more convex. Okay, so now that we know that, this suggests that, well, we can just train a kernel, so optimize the kernel using the same function. And for example, this is what was proposed by Gertland-Create and colleagues in 2004, where they say, well, suppose you start with m different kernels and you want to combine them, for example, by forming a convex combination, meaning forming a weighted sum where the weights are non-negative and sum to 1. So you want to add the different kernels together with some percentage. Then a principled way to learn the etas is just to write the optimization problem that you solve usually just in F, but minimize also in eta. Right? So here you would have a minimization in eta and for given eta in F in the RKHS of k eta of your SVM loss or of your kernel ridge regression loss. The problem now is jointly convex, so it's a minimum of a minimum, so it's a joint minimum. It's jointly convex in eta and alpha and can be solved efficiently, right? So when I say efficiently, in fact, check the paper. There are different ways to do, but this can be written as some semi-definite programming problem, optimization problem, and so there are ways to solve it. So when you do that, it's called multiple kernel learning. And so you see that MKL, the standard definition of MKL, is to learn a convex combination by just optimizing the weights using the objective function of your standard kernel method. It turns out to be quite successful in some cases. So let me mention a couple of classical papers that do that. So this paper is again an example in bioinformatics where the goal in that paper was to predict properties of proteins, like the function of a protein. They considered a bunch of different kernels. So here on the plot, you see different columns corresponding to different kernels, whatever they mean. Some are based on the sequence, some are based on the network, some are based on the expression, etc. And I think the thing to look at is that the first 7 bars, so all the bars except for the last one in the top, give you the ROC, so the performance of each individual kernel. So you see that some kernels are better than others. And the last column is the performance you get once you combine all the features together, so all the kernels together with MKL. And so you see first that the performance is better, right? The right bar is higher in terms of ROC than the individual kernels. And the bottom plot, called the weights, shows you the weights of the different kernels. So you see that in that case, MKL converges to a solution where you don't have uniform weights, but where in a sense, if you look closely, it's not always true, but the individual kernels that tend to have good performance, like the dark one here and the red one, tend to have also large weights, right? But it's not, let's say the weight is not a function of the performance. The weights have been optimized so that the weighted combination gives the best possible performance of the training set. There are other examples. I think I showed this figure already in the lecture about graph kernels, but here, I didn't mention it, but here there are different kernels which are compared. So these are kernels for images, so one based on histograms, one based on a graph kernel, a subtree kernel, weighted subtree. So the left, the 4 kernels, so the 4 performances from the left correspond to individual kernels. So we see that there are differences. For example, here the WTW kernel is better than the other ones. But the last performance, which is even better, is MKL. So it's a multiple kernel learning that was applied to the 4 kernels here. Right. So again, this is a case where you can test different kernels, in this case for images. And at the end, if you combine them, for example, with MKL, you obtain even better performance. All right, so MKL, as we described, when you have different kernels, you can make the sum, you can make a weighted combination, and you can even learn the weighted combination to obtain what's called multiple kernel learning method, which, I summarize here, optimizes k eta over eta. Now we can go a bit further to understand a bit more what happens when you do MKL and maybe reach some kind of surprising reinterpretation, but which gives a lot of insight. So basically, I'm going to present some work that was done in particular by Francis Bach a few years ago that basically starts from the formulation of MKL. So saying, what I've explained so far is that MKL is a minimization over the weights and over the functions of the standard objective function of kernel methods. And what I did not say yet, but what's written here, is how you can reinterpret that in terms of Rkhs and regularization, right? When you minimize over both the kernel and the functions, can you explain it as a single optimization problem over functions? And so this is what Francis Bach and colleagues did, and they showed that this MKL can be rewritten as a minimization problem over functions in each Rkhs of the risk of the sum. So it looks exactly the same as when we used the unweighted sum kernels. We also had a minimization over f1 to fm of the risk of the sum, plus lambda regularization. But here there is a small difference, which is super important, between the regularization we get for MKL and the regularization we had before, is that for MKL, the regularization is the square of the sum of the norm of Fi. So I think it's worth comparing that, and we will do it a bit later, but to what we had before. I'll come back a few slides earlier. When we had the sum kernels, we said that if you train just with the sum kernel, then basically you learn a sum function which minimizes the risk of the sum function, and a penalty, which is the sum of the squared norm of Fis. Now the new theorem says that when you train an MKL model, so there is some eta, but at the end of the day, what you do, there is no eta anymore here, right? We will explain why. What you do at the end of the day is also train a function which is a sum by minimizing the risk function of the sum. And here, instead of having the lambda times the sum of square norm of Fi, there is no square anymore in the norm of Fi. You first do the sum without the square, and then you square the sum. Right? This is the only difference between training with the sum kernel and training MKL. Right? So it's a bit surprising. I mean, if the first time you see it, sounds a bit surprising, because in the sum kernel, the direct and intuitive interpretation is that what we do is just optimize the weights, eta, and then just train with one weighted kernel. But in fact, we will see that when you optimize the weights and when you optimize the etas over this particular convex set, which is a simplex, then you can basically explicitly show what the optimization is and deduce that the real objective function in terms of functions Fis that you do is just replacing the regularization from the sum of Fi squared to the sum of Fi squared, right? And the difference is where you put the parentheses. All right, so actually the proof, it's a super interesting result, but the proof is not too complicated, at least with the proof of this theorem. It just amounts to, to be careful about what happens when you minimize over eta. So let's do it together. Remember that MKL minimizes over eta and over f in h, the Rkhs of k eta, the standard objective function of kernel methods. Right? So here what we do first is, remember that we showed a few slides earlier, what is the Rkhs of k eta and what happens when you train with k eta. And so we said that when you train with a weighted kernel, so when you fix eta and you train over the Rkhs of k eta, it amounts to minimizing over functions f1 and fm, which are in the different Rkhs, the risk of the sum. So here the eta doesn't play a role. The only thing where eta played a role was in the penalty. So when you choose different etas, you have different penalties And the role played by eta is to replace the sum of fi squared by the sum of fi squared over eta I. Right? So something interesting here is that you see that the space over which you optimize does not depend on eta. You always optimize over functions f1 and fm, which are in the Rkhs. And the risk term does not depend on eta either. The only contribution of eta when you optimize over eta is to modify the regularization. So this means that you can minimize, it's a joint minimization. So you see that you can also rewrite that by first minimizing over eta and then minimizing over f. And this suggests to put the minimization in eta where there is some eta, meaning you need to minimize over eta the sum of fi squared over eta I. And here comes a trick that actually, Francis Bach explained to me many times, which is just a simple trick we'll see next slide, which shows that, which tells basically that the minimization over the simplex, so here it's important that eta is in the simplex, and remember the simplex is a sum of non-negative etas that sum to 1, so the set of vectors that allow it to make a complex combination. It's a fact that the minimization over the simplex of a sum of fi squared over eta I is equal, you can do it explicitly, is equal to the sum of the norm of fi without square, and then you put a square to the sum. Right? So in a sense, you can explicitly and by hand, and I will show it in the next slide, minimize over eta. Right? So there is no magic here, but this shows that initially, I introduced MKL, and even the initial MKL paper presented it as a way to say, well, we want to optimize a combination of kernel and then learn with the optimized kernel. This is true, but this way to look at it is a way to reinterpret what MKL does and say that when you optimize over eta, what you do at the end of the day is just you optimize over the same set of functions. So you're looking for a sum function. But what you do is just you change the regularization, meaning that instead of penalizing a function by the sum of the squared norm of fi, you penalize by the square of the sum of norm of fi. Right? So let me just add to this the eta trick. If it's the first time you see it, just try to prove it. But it just says that for any set of functions, it's not related to the fact that you have norms, etc. It's just that for any vector of non-negative numbers, so if you have a set of non-negative numbers, you can check that the square of the sum can be written in some variational form as the infimum value over the simplex of the sum of ai squared over eta I, and this is just a direct consequence of Koshy-Schwartz inequality. Right, so here this is what we use, right? We have a sum, so a minimum of a simplex of a sum of a square number over eta I, and we just call this ai and replace all these by the sum of ai squared. Okay, so what are the consequences of that? Well, a first consequence, a first comment is that when you want to implement MKL, then there are different ways to do. I said the initial paper rephrased it as semi-definite programming over matrices, etc. I think that the simplest and most elegant and fastest, in fact, method is just to see it as a minimization problem over eta and gamma individual of this function, where you see where the eta plays a role in the kernel matrix. And just to use basically a standard solver. So for example, in the course, you may have implemented by yourself kernel ridge regression or kernel logistic regression, or you may have implemented or use a software for support vector machines. So all these softwares, what they do is that for a fixed kernel, if you fix eta, then they solve that. They solve the dual problem. So basically, they give you the value j of k eta, right? And so the question is now, if you want to optimize over eta using a numerical method, for example, gradient descent or projected gradient because you have constraints on eta, what you need to be able to do is not only to compute j of k eta, but also the gradient in the kernel, so in eta. It turns out that once you have solved the SVM, then the gradient, so the value of j is given by the value that you've computed, and the gradient in k eta, that's a generic theorem that tells you that the gradient of j in the kernel is just the matrix, so the coordinate, so the gradient, sorry, with respect to eta I is just minus lambda times gamma star ki gamma star, right? So this is standard results, and so this shows that in fact, when you want to numerically optimize eta, you can develop an iterative method where you start from some eta, for example, uniform eta. You solve your kernel method to obtain the dual variables gamma. Then you have the value of j, and you have the gradient in eta. So you can change eta and then solve it again and again until convergence of the eta is to the best smallest value in j. All right. Second comment is let's discuss a little bit more about the result that I mentioned of Francis Bach and colleagues about reinterpretation of MKL as a different penalty. So here I just rewrite once again to make it clear the difference in terms of mathematics, what optimization you solve when you train with a sum kernel. So just you have n kernels, you put them together and solve your SVM, for example. Or what happens when you do multiple kernel learning, meaning you have this iterative procedure that optimizes the etas until convergence. And at the end of the day, it seems like you have solved a single SVM, but with a weighted kernel. So what we've seen is that the two problems solve two optimization problems in the RKHS, which are quite similar and only differ by the regularization, which is either the sum of the square norms or the square of the sum of the norms. Okay. So one thing to what you might ask, so does it matter? I mean, is there any difference between the two? In both cases, you want the norms of the FIs to be small, but actually there's a big difference, and I will not spend too much time on it because either you know it or you don't know it. But the main difference is that in the second form, so in the MKL formulation, the regularization you use, which is a sum of the norm, is not smooth, right? Because the square norm is a smooth function, but the non-square norm, has a peak in 0. So if you plot the value, so over the space of functions of the non-square norm, it's not smooth in 0. And one consequence of that is that when you solve the second optimization problem, you can show that there are many configurations, so you can express this in terms of probabilities over the points, but where in the solution, many or several of the FIs will have exactly 0 norm, right? So it's a non-smooth optimization problem where you can show that because of this regularization, I said, the external square is not important. You would basically have the same problem or the same optimization problem if there was no square, because in both cases, with or without a square, what you solve is, you can rephrase it as some constraint optimization problem where you minimize the risk of the function, subject to the fact that the penalty is bounded. And so the penalty, you can write it as the sum of norm of Fi or the sum of norm of Fi squared. This gives the same set of constraints, right? So think of the second square in the MKL formulation as not important. It's not necessarily there. And so when you look at the sum of the absolute norm of Fi, this is a non-smooth function of Fi. And so when you do this optimization problem over this set, you can show that the probability that it reaches a solution where some of the FIs are exactly equal to 0 is strictly positive, right? And so in particular, when the different kernels are linear kernels over different representations, then the second formulation has a name. It's called group lasso. So this is what I said, either you know it or you don't know it, but I assume that you may have already heard about lasso regression. Lasso regression is famous for being a way to train linear models which are sparse, right? So it's a lasso regression is a regression when you train a linear model, but when you use a L1 penalty instead of a squared penalty, so that the model you train has many zeros. So it's supposed to be good to, when you believe that there should be zeros. And in fact, what we do with MKL is the same, except that now instead of being sparse over features, you penalize the function so that you are sparse over the kernels, right? And so moving from lasso, so individual features to functions, as a name, if you have linear model, it's called group lasso. Right, so as I said, so you can check this slide, but as I said, if you take linear models, or even more, if each kernel, suppose you start with data which are vectors in d dimensions, and suppose you say, well, I create d kernels, and each kernel, ki, is just the inner product for dimension I. Then I let you do the computation by yourself, which is basically written here. But in that case, you can show that doing the sum kernel is equivalent to doing squared, so ridge regression, right? Like when you sum the kernels, it means that the kernel is the sum of xi prime, so it's just the standard inner product. And so when you do kernel ridge regression with the standard inner product, you get ridge regression. But if you do multiple kernel learning over these kernels, then the second term becomes the sum of the fi norm without square. And so in that case, the norm of fi would be the weight of the model. So you obtain lasso regression. Right? So again, in the extreme case where each kernel corresponds to one feature, then the difference between sum kernel and MKL is just the same as between ridge regression and lasso regression, which for most users just amounts to saying, in both cases, you regularize. So in both cases, it can be nice in high dimension. But the main difference is that you do lasso regression when you expect your model to be sparse, in the sense that you expect to recover a solution beta that has many zeros, right? So this is just for this particular case, but the more general case you can show, and I don't prove it, but there are many papers that do, is that MKL, written this way, should be thought of as a group lasso penalty, and therefore as a good model if you believe that many of your kernels are not useful, so that the model you train will have many of the RKHS set to 0. So the Fi would be equal to 0. So the good configuration for MKL is typically when you start from many candidate kernels, and your prior belief is that most of them are not relevant, so that MKL will select a few of them. Right, so I insist a bit on that because I think that's one of the misconceptions shared by many people in how they understand MKL, and it's partly because of the way it was introduced, and even the way I introduced it in this course. MKL was initially introduced as a way to say, let's be a little bit smarter than just doing the sum, and weight differently the different kernels, to say that maybe one kernel should have a bit more weight, or some other kernel a bit less weight, so that we're a bit better. But when you see it this way, in fact, what you do is not only to rewrite the kernel, it's just to bet on sparsity and train a model that would be a sparse combination of kernels. Right. A last comment, maybe. Yeah. A last comment is that there exist many extensions of that work, and I will just mention one of them, which, if you're, if you like it, you can try to develop by yourself. Is that here for the moment I just focus on the MKL when we make a convex combination of kernels using using the simplex, so the set of etas such that the sum of eta I is equal to 1. And so there exist many extensions, but I will just mention one of them, which allows to create different, we'll look at the theorem, but which allows to create different penalties that somehow interpolate between lasso and ridge, so interpolate between the two extremes that we have seen. And the trick is, or the recipe, if you want, is to change the simplex, so the set over which you optimize, by looking at the simplex to the power r, if you want. So it's just a set of non-negative vectors etas, such that the sum of eta I square is equal to 1. Right? So depending on how you pick r, this can give you something like the simplex when r is equal to 1. If r is larger, this becomes more a part of the sphere. You can be non-convex as well. So I should say, the only configuration when these objects is convex is when R is equal to 1, so you may have some non-convex issues there. But mathematically, at least, you can show that if you choose a R and optimize over this space, so if you consider, again, the best eta in that space, sigma R, in terms of the function j of k, so the objective function of your kernel method, then you can write the same theorem as the one I showed before that explains the regularization effect of MKL, but this time with the term R. And basically, you obtain the same flavor of equation where the optimization over eta translates into minimizing the same risk. So you still minimize over the same functional space, which is a set of functions f star, which are sums of fi star. So it's always the same space of functions over which you optimize. But you modify here the penalty. And you see, in this slide, I put in red the exponent. So the only thing that's different is the exponent. And in particular, so if we forget about the external impedance, so the exponent outside of the parentheses, because as I said, this one is not very important. The one that matters is the exponent of the norm of fi. And so if you pick a given positive R, then the regularization you create is the sum of norm of fi to the power 2R over R plus 1. Right, so for example, when you take R equal to 1, you obtain 2 over 2, which is 1. So this is MKL. But you can obtain different values, and in particular, you can obtain larger values or smaller values when you play with the R. All right, so I will not go further with that, but this is just to show that, in fact, there is a lot of things hidden in the choice of the space eta over which you optimize. It's not as simple as saying I will just find a good combination, a weighted combination. In fact, when you write MKL and you play a bit with the space over which you optimize, so what are the combinations you consider, you can directly translate them into specific regularization in some RKHS, which may or may not correspond to prior knowledge you may have. All right, we'll stop here for today, and the next section will be about other topics, in particular large-scale learning with kernels. Thanks for your attention.